doing today? Alright. Let's stop it right there. Oh, where did it stop? It's okay. Pick it up. Alright, how you guys doing? Yeah, just made a quick song for you guys. This is the last video I'll probably be doing for this class. I did tell you guys last video that if I had time I'd make another one, and I have more time. So here we are with our other video. By the way, I'll probably present a little more surprise for all of you who really like this signals and systems stuff. But let's go to the main point of today. By all popular requests, everyone wanted a study session for some reason, or examples to go over. So today we'll be going over more stochastic systems and signals and systems and probability. So one thing we didn't go over was, well, the actual definition of probability. And probability is basically, well, if you had a coin, well, what's the probability that one side start is this and this? The probabilities all should add to 1. Remember the cumulative distribution function? When you integrate all the probabilities, they should equal 1. So right now what we're going to do is we're going to play a game. And then you're saying, games? We'd have no fun in this place. You're wrong. This is a special game. We're going to make an unfair game. And we're going to create one. Just going to create one on the fly. Let's create a game where let's call our sample space is equal to, let's make an X, circle, triangle, and square. And if you don't know why I chose these ones, it reminded me of me playing my PS5 later today. Just kidding, I don't have one. But okay, we're gonna have these 4 sample things. So think of it like, okay, 4 items that we have. What's the probability of this and this? What we're gonna do is, I want to set a root probability. So let's choose this triangle to be our root. We're gonna make everything in terms of this probability of a triangle. So what if I said the probability of X, or item X, is going to equal 1/4 the probability of triangle. Let's do that. So we just created a space, and we want to make this unfair. So one of them is going to be more likely to happen than the other one. And I think in this terms, we're setting everything as a partial of the probability of the triangle. So that means our triangle is going to be the one that dominates. So let's make the probability of the circle. The probability of the circle, okay, remember my words. The probability of this item is 1/8 the probability of another item. So this is how you do it. Don't switch the other way around, else your game's gonna work the opposite way of what you think. So remember that. The probability of this square is going to be 3/8 the probability of this triangle. All right, and remember what I said when all the probabilities should add up? Well, they should add up to 1, so just do this. Let's do another marker. The probability of the X plus the probability of the triangle, circle, doing it in order, I put OCPD. Probability of the triangle plus the probability of the square should equal 1, okay? So just plug and chug. We're going to try and solve for the one variable that we're trying to solve for, the triangle. That's the one thing that's in common. So let's do 1/4 the probability of the triangle plus the circle is equal to 1/8 the probability of triangle plus the probability of the triangle itself plus 3/8 the probability of the triangle is equal to 1. And then you're probably saying, won't adding all these up be something greater than 1? Yes, but we're not we're worried about the variable, our variable p of the triangle, the probability of the triangle. So we're going to solve for it so that this entire side will be forced to equal to 1, okay? So don't worry if you see that on the exam, you're like, oh, I have a big number on this. No, don't worry. We'll get there. So the probability of this triangle is equal to, well, let's bracket 1/4 plus 1/8 plus 1 plus 3/8 is equal to 1, okay? And then just do your addition as normal. Let's do the probability of the triangle is equal to, oh, no, let's not skip steps. So this right here will make 4/8, which is 2/4, plus 1/4 is going to be 3/4. 3/4 plus 4/4 is going to be 7/4. 1. Therefore, the probability of the triangle, the actual probability, will be 4 out of 7. And now you're saying, okay, just plug it in. And then we'll get the following. The probability of the triangle, or x, sorry, is going to be 1/4 the probability of the triangle. You see this 4 on the top and the 4 on the bottom should give you 1/7. The probability of the circle is going to equal 1/8 the probability of this. So we can do, I'm going to skip some steps. Do that in your head. Probability of the square is going to equal, okay, we have a 3. 4 divided by 8 is going to give you 1/2. 2 times 7 is 1/14 times 3. 3/14, and there you go. And now the probability of your triangle, you already know that. 4 divided by 7. An unfair game. Pretty fun, right? Want to play? Let's play a game. This is where the real fun happens. Let's assign an event. Let's play an event. And I think he calls the event an event. This, the probability of whatever you have in the middle. So that means let's map one event. We want our game to be very unfair. So let's make the higher probability the one where you lose a lot. So let's make it probability of our triangle is going to equal, let's make it to lose minus $10. There we go. Then let's make the one where you win the least, this 1/14. The probability of the circle is going to equal, let's make it where you just win $10. The probability of, let's just randomly assign some stuff, not too hard. Probability of the X event is going to be, let's make it 5. But do I want to do that? That's fine. We're just doing an example. Probability of square is going to equal -5. Right? We're just making money. You can make these any numbers you want. You can make it 1, 2. Just choose numbers you can do in your head. Right? So now we have our game. But what's the expected outcome? So basically, the expected outcome is if you were to do this infinite times, well, what will you eventually get? What's the average, the expected outcome? So let's grab another piece of paper and let's do this. 2. We're still recording, right? All right, we're still recording. Oh, there's a mouse in the middle. Okay, there you go. So the expected value is going to basically equal, well, whatever probability you had at X. Think of the probability of an event, the probability of something times the event mapped to it, to that probability. Just do this, plus probability of circle, X a circle, I'm just going to shorthand this, plus probability of triangle, X a triangle, plus probability of the square, X of the square. There we go. And then all you do is just plug and chug. You already have all your probabilities and all your events. Just map them all together. So the first one's going to be 1/7 times the probability. We've just made it to where you can lose $10. Plus the probability of the circle is 1/14. Times the probability of circle. We made it to where you win $10. Okay. Plus the probability of this triangle. Triangle itself is 4/7. So wait. No. Oops, sorry. I was mixing my head. That looked like a triangle first. Okay. Here's our x. Here's our event x. Here's our event x. 5. Sorry. That's my mistake. Circle, we mapped that to winning $10. Probabilities right there. Now we're going to do this. Okay. The probability of the triangle is 4/7. Okay. Then the money we win from this triangle is -10. There you go. Plus the probability of the square, which is 3/14, times the money we map to the square, which is -5. There we go. And then all you do is just simple multiplication. 5 times 7. Oh wait, let me see. What did we map to this? Yep, okay, that should be fine. Plus 10 divided by 14 minus okay, we're gonna have to do this. It's gonna be painful. Minus 15 over 14. If I were to do the math, minus 35 over 7 minus 5 over 14th, which is equal to, if I were to double that, minus 70 over 14 minus 5 over 14. It's equal to 75 over 14. Yeah, there you go. And if you were to do that in your head, nah, it's okay. You can leave it in fraction form. Should be fine, unless you have a calculator. I think there's no calculators on the exam. But point is, you see how you play our game, you always lose money. So that's a great sales pitch if you wanted to work in the casino industries. There's one thing I forgot to mention, and that was, hey David, how do we verify that our things add up to 1? If you add this 1/7 plus 1/14 plus 3/14 plus 4/7, if you look at this 3/14 plus 1/14, you get 4/14, which is 2/7 plus 4/7, that's 6/7 plus 1/7, which is 7/7. There you go. So that's how you verify that you've done it right. Make sure you do that. So it's a checker. So let's see. The next thing I want to go over is, let's see. There we go. So remember what I said about signal to noise ratio? Let's try to do this. Signal to noise ratio, SNR, which is equal to, we're going to call the power of our signal divided by power of noise. So remember what we called power? Power is another way of saying zero mean variance, or other words, well, the variance with the mean of equal to 0, which means we're actually looking at the variance of a signal divided by the variance of noise. So when you're doing SNR, it's not just power, it's variance. Power is a special definition of variance where we have 0 mean. So that's for periodic signals. So let's see, if I were to give you the example of, yeah, let's just do this one. If I were to give you a time system, y of t is equal to cosine t plus some signal, let's call it x of t, where, let me see, let's just do a noise generator, let's have some fun, where our x input is going to be some noise generator. And note, this can change So memorize that. Let's just make it from -1 to 1 and alpha. So that's our little thing. This is our probability of the signal itself. I don't think you're going to be thrown a triangle, but if you were, yeah, you just do an integral. You know how to do that. But this is how you would do it. We're assuming a zero mean. Okay, I said the answer. Our signal is going to have an average of 0. Our inputs, our noise is going to have 0, a mean of 0. So if you wanted to solve for this alpha, you're going to have to solve for this. You can do it two ways. You can either do it by, you know that if you go from -1 to 1, you're trying to find this alpha, which is equal to, actually, let me just go over the actual definition. From A to B, the probability of x. So we're looking at the probability of x as a function of, well, the value itself, which is equal to, actually, the value of itself at a particular time. Don't worry. This is equal to 1. This is your holy rule, okay? You got to memorize this. Okay? But we just called this P of x, this probability curve, alpha. Therefore, -1 to 1 of alpha, dx is equal to 1, which is also equal to alpha x, which is going to be from -1 to 1 is equal to alpha 1 minus -1 is equal to 2 alpha, which is equal to 1. Alpha is equal to 1/2. There you go. Ooh, that always takes me off. You can either do it this way, which is the formal way, or you can do base times height, get your square. So 2 ways of doing it. So now that you know this, now you can start actually working on it. What is the mean of our zero mean noise? So if we were to look at the mean of something, you literally look at, well, you already know. Okay, so we're going to go from A to B of this probability curve of x times x dx, which is equal to, so this P of x is this. This is also our P of x, which is constant. So that's what we solved for. Alpha -1 to 1 x dx is equal to alpha x squared over 2 -1 to 1, which is equal to alpha 1 over 2 minus -1, which is squared to, the square term makes this positive, which means positive minus positive gives you 0. So now you know the mean, right? Zero mean noise. And now you're saying to me, what is the output power of what's the output of the power of our output? We already have our output. The output is equal to, well, our signal, whatever comes out, plus whatever noise comes out, the noise signal. So let's try to do it like, how do I do this? Let's use another piece of paper. Here we go. How are you guys enjoying this video? You guys even watching this? Okay, y of t is equal to cosine of t plus x of t. So if we wanted to know the actual the output power, which is variance of y, which is basically equal to, how do I do this? Let's see. Let me remember it. Actually. So let me go to this special trick we know. Mean of y is equal to the mean of x times, no, do I even want to do this on infinity to minus infinity of h? Since we have noise, and since this is periodic, we already know our mean of the output signal is going to have to equal 0 because the mean is 0. That means our output is 0. The variance of y is equal to the mean squared y squared minus the mean of y squared. Since we defined the mean of y 0 because the mean of x is 0, the input signal is 0, all we got to do is just solve for this e of y, which is going to equal, because it's periodic, you can go from negative time to infinity time, but we're just looking at y. Cosine's a periodic signal, so let's go from minus 1 or pi to pi. However, because we're doing a mean squared, we're adding all these points, but to get the mean you have to divide it by the amount of points there are. So it's a weird trick to explain. It's how do I explain it? Cosine and wait, I'll get it to you guys. T. So the formula, if you wanted to know the average power, actually this actually might even be the power, which is equal to 1 over t from delta t minus delta t to positive delta t of your actual signal squared, which is sine squared t, whatever you want it. This is like our little holy rule of signals and systems, or power. It's however long your time is. Oh yeah, dt from minus delta, I'm just going to shorthand this, x squared of t dt. So this is like your holy formula for calculating the mean squared. Okay, the mean comes from this. Actually, the mean comes from this, and then the squared term comes from this. So that's how you think about it. And then if you want the RMS, you would square it, okay, or square root it. So let's go back to this. Since we already defined this as 0, all you got to do is just do the following. Minus, no, that's not minus, plus 1 over 2 pi cosine squared, let me remember. This one's up, actually, I think I got this one. Do I know how to do this one? Hold up. Cosine squared. No, I can do this. Come on. 1/2 plus cosine 2t. There we go. Minus. Oof, I have to remember that one. It's equal to 1 2 pi. Because would it bother you guys if I did this? There you go. That can be pulled out. Wait. No, because no, we actually haven't taken the integral. I'm so sorry. We're still doing this integral. 2 pi of the integral of minus pi to pi 1 plus, oh wait, another half has to come out here, cosine 2t dt, which is equal to 1 over 2 pi. Don't worry guys, I got you. The integral of this one is going to be from pi minus pi minus pi divided by 2, and then that cosine term is going to go from, because it's periodic, I want to skip steps but I shouldn't. Okay, cosine integral cosine is going to be sine of 2 pi minus sine of 2 pi. There we go. And this one also has a 2. Sine of 2 pi is 0. Sine of minus sine of 2 pi is also 0. So this term and this term are going to equal 0. Point is, when you integrate a periodic signal and you try to find its average, you're always going to get 0. That's something I was trying to shake my head on. But what we're looking for is, this is the term that pops up. 1 over 2 pi. 2 pi divided by 2. This cancels out, that cancels out, that cancels out. 1/2. Whew. Man, that puppy was hard. And yes, this makes sense. What is the average power of a sinusoid? It's its amplitude times 1/2, or if its voltage is equal to 1, that means the power of cosine or sine is 1. Oh man. So much brain power, y'all. This is 4. Okay, so now that we have this power, variance. Now let's do our SNR. Keys. Oh, we're already at 26 minutes. Sweet. So SNR is equal to the variance of our whatever's at our output divided by, is that out? No. Yes, our output. We're looking at the power at whatever we see at the output. I was going to say input too, but don't worry about it. To the noise, which is basically equal to 1/2 divided by, what did we say the noise was? Where's our noise variance? Did I never calculate the actual power of the signal? Okay, we're forgetting one more term. Power of the noise itself. And we just said power of the noise. We're just going to look at our probability curve. And we actually have 1/2. That's our amplitude thingy. Yes, that's our amplitude thingy. It's the probability density function amplitude from -1 to 1 of x squared dx. It's going to equal, I think these numbers should be familiar, 1/2 x3 divided by 3 from -1 to 1, which is equal to 1 over 6. 1 minus 1, which is cubed, and that makes it what do you call it? It still keeps it negative, which means negative and negative turn to positives, which means it's going to be 1 over 3. There we go. That's our variance of the noise. Therefore, 1/3, which is equal to, well, I can't do this head. There we go. 2, 3 over 1 is equal to 3 over 2. Not that bad for power, or our signal to noise ratio. Your answers may differ. Actually, we're just looking at a different noise one. I'm just generating random noise. You'll probably get a different number, and you will get a different number if this changes, okay? So make sure he can change it on you to where it's 1/2 or it's 2. It can be whatever he wants it to be. So, and based on what I have, if your amplitudes are too big, let's think about it. If we have a cosine, think engineering. If we have a cosine to 1 voltage, and our noise is literally like going from 30 to -30, that's a big noise, right? We expect our SNR to go bad, really bad. We have this noise that jumps up, and then we have this sinusoid that's just 1 volt. So therefore, think about it. If our thing is 1/2 to -1/2, or it gets smaller, we get this small noise, which means SNR boosts up. So that's a practical engineering tip, just in case you start fumbling up. So with this kind of noise, actually it's not that bad. We're getting pretty good signal. But if this were to widen up, and you can redo this problem, try it for 1/2 and try it for 2, and you'll see the difference. You see that the wider this gets, you're gonna get bad SNR. So that's another example you can do. So the next thing I want to do, and so what if, and I'm probably just gonna let you guys do this on your own. What if he does this to you? He says, okay, we're gonna give you noise, right? X of t. However, noise is gonna be a transient that just bounces up like this from 1 to 0. Therefore, its probability density function, it's P of x, is going to go from 0 to 1, and it gives you like a constant number. Just call this your alpha. You know what to do. Solve for alpha. You can use your handy dandy 1, which is equal to 1 times alpha, which is equal to 1. There you go. Now you can solve for that. You see, it's all coming to sense. However, when you're solving for this mean of x, which is equal to, well, the value at the front, value of alpha, from 0 to 1 of x dx, which is equal to 1, and then x 2 from 0 to 1/2, which is equal to 1/2. You note that you have a mean value. So what this basically means is, if you were to calculate the variance of your input signal, which is equal to the mean squared minus the mean squared, you actually need to have to know this. This is where Dr. Stever would catch those who know what's going on and don't know what's going on. So you have a mean, your variance is not going to have a 0 mean. You have to put this into consideration. This should be easy. So if you don't memorize this, you will cry. You will definitely cry. So, and you already know how to do this e to the x squared. X is squared inside the e. So you know how to get that one. But for your output, should be the same thing too. If you were to find your variance of your output, if you were to give you a y of t, which is equal to, I guess, x of t minus some constant, all you gotta do is just y squared. Just punch in that y right there, and your boundaries are just going to be basically for, if our output is equal to our noise minus some DC voltage, you're just going to have this, well, bouncing signal, and shouldn't be that bad. You guys should be fine. So if you don't know what I mean, your bounds are going to be from this were 1. That means the integrand is going to go from 0 to 1 for this guy and this guy, because we're looking at the bouncing signal. So I don't know how to explain that without revealing too much. You guys would be fine. So this should be all like pretty simple stuff. So 4. Man, I forgot to bring another water. It's a little hot in here, but it should be okay. Alright, this should be my final page. So now our final thing that we're gonna do is let's see, if we were to do this one, well, there's one thing I gotta tell you. So remember in the Laplace transform, if you have this type of pole mapping, let's call this one minus alpha, where the Laplace transform is going to equal 1 minus, or 1 divided by s plus alpha, which means if s is minus alpha, you get your pole right here, okay? So this is your general equation, the inverse Laplace transform. Inverse Laplace f of t inverse is going to equal an exponential alpha to the t, u of t. Don't forget the u of t, okay? And with the z transform, where you notice you have a unit circle now, it's gonna go around like this, where the pole has to be inside. So let's call this one alpha, and this is going to be the z, f of z, I think, capital F, is equal to 1 over 1 minus alpha z to the minus 1. And I think that makes sense. When this is equal to alpha, positive alpha, then that will give you 1. Okay, there we go. That means f of n, because we're looking at the time domain, is equal to the pole to the n, parentheses that, u of n. Okay? So these are your general equations. I don't know which one he's going to throw at you, a Laplace transform or a z transform. Actually, let's go more into depth. Use these markers. Remember the residue theorem? The residue theorem is basically if you have a complex system, you have like a 1 over s minus p1, s minus p2, that you can turn it into alpha s minus p1 plus beta, or b s minus p2. This is the residue theorem. Whatever is on your top is your residue of the pole. And then you can just do a simple Laplace transform or z transform inverses. And then the puppy of this show is, if I were to ask you to find, oh yeah, I forgot, all these variances need to have a squared term. I should probably do that, because we're looking at a squared value. The variance is a square. It's equal to x squared is summation h squared, and I'll just leave it like that. Okay. There we go. Or y squared there we go. So you have two equations you can either use. You can either use this one for, I should have flipped this around, for the z transform. But you're not going to be doing any z transforms or discrete. And then this one right here is going to be for Laplace. Form or analog. There we go. Or continuous is continuous. So point is, if you have an h of t, or whatever your function of t, if you were given h of t of something, all you got to do is, if suppose h of t is equal to e to the minus t, we're just going to make the residue 1, alpha is 1. It's going to be a pole literally, well, right there. It's not going to be that. If u of t, that means h squared of t is equal to e to the minus 2t u of t. And if you were to punch this into the integrand, all you got to do is solve for this. That's it. And I assume you guys can do that. And I think this exam shouldn't be that bad. I think you guys all have it in the bag. I'm looking at my previous notes, and honestly, it's just practice. You just got to know how to do this. If you can do this, if you can do these poles, if you can do this, and you memorize this holy rule, the mean squared minus the mean squared, and SNR, and I think you should be golden on this exam. So yeah, it's not that bad. Let me see. Actually, there's one more thing. Suppose you were given an output. I should go over this. Because I was confused back as an undergrad too. Okay, let's punch that puppy in. 6. If you were given that same function h of t, which is equal to e to the minus t u of t, and you were asked to find the mean of y, You already know this one. Mean of x times the actual h of t from minus infinity to infinity. You would think you would have to do from, let's say if the input signal was, well, from, if our input signal is from -1 to 1, you would think you could do this. You can use these bounds, but when we're doing the mean, we're not looking at the bounds of x, we're looking at the bounds of the actual h response. So this is the one that you'll probably get confused with. Don't forget these infinity signs, it goes with h of t. So formulas you would have to memorize would be, well, memorize, it's common logic, is this one, and maybe this page too. The mean squared minus the mean squared, SNR, and variance. Well, yeah, mean squared minus mean squared. And I think this exam should be cake. From my year, everyone got a really good score on this one. So I think this exam is more like who actually paid attention. So with that, I think we're good for now. And it was a pleasure to teach you all this semester. And if you were to go into EE480, what you guys would be covering would be, well, you guys would go more into the Z transform. So remember what I talked about with DFTs and DTFTs? Discrete time Fourier transform. I was thinking about something else. So the DFT would literally be, well, we're just looking at just like amplitudes, like we're looking at a summation of discrete things. They're all periodic. However, this discrete time Fourier transform, we're actually looking at from minus pi to pi. That's a complete period, actually 2. There we go, 1 period, where we might look at, like, you know, some function like a sync wave. There we go. And it's periodic. So that's a discrete time Fourier transform where the bounds are this. And if you wanted to make it a Fourier transform, well, you would take these bounds to infinity, I think. Don't worry, you'll focus more on this, and then you'll go over sampling, aliasing, and like, oh, like what happens if you have an input signal and you have to go over f of s, sampling frequency over 2, and the frequency itself, sampling frequency. You go over a lot of things in that class, but what else do you go over? You will build lots of filters, so, or not filters, you'll go over a lot of sync functions. So do recommend taking that class. So or if you don't go the 480 route, you can also go the 370 route. They go more into control theory and the Laplace, but I'm not gonna touch that. But I do recommend going into 480. So with that, I would like to go over one little thing. Let's see. Oh yeah, this right here is a Fourier transform. I'll probably explain a little bit more. So actually right now, if you have to go do something else, you can go have fun. But let's, actually I want to play a song for you guys. This is all completely optional, everyone. There we go. Plugins. Analog. There you go. Oh. X. Go. Demo. And liked. There we go. Alright, let's have some fun, everyone. So actually, yeah, this is a Fourier transform. This is a real-time signal. That's a more sampled signal. If we were to sample a bigger window, you get more information. However, you do a smaller window, you get less information. And actually, this is a pretty cool pattern. This is all, if you add all this, you get this time representation. So let me play my song. wanted to play. But actually, let's do one more thing. So, oh yeah, I made this song. It took me a while. That's why I didn't post it a video yesterday. Yes, this is all completely optional. Okay, let's build something. I want to build you guys the reason why the Fourier transform is so amazing. That right there is a pure sine wave. Okay, and you see how you can see it? This is practical engineering right here. Okay, there you go. Let's put that away. See that sine wave right there? These are literally direct deltas. If you were to flip the plane, which I can't do it because it'd be too much rendering. Oh yeah, this is a faster sampling, this is slower sampling. Let's create a triangle. So let's add a little amplitude to this note. There we go. There we go. Let's add this one. There we go. There we go. Looks kind of like it. Ah, there you go. So we're trying to make a triangle wave from a sine wave. But that's basically so, alright everyone, that's all I wanted to show you for today. It was a pleasure teaching you guys. So, hey, take care. Oh, let's finish that song.